All right, so now we're going to introduce two terms that are really, really important in organic chemistry, and this is this idea of a nucleophile and an electrophile. Most all organic reactions take place because a nucleophile is reacting with an electrophile. So let's just introduce this terminology real quick. Again, sort of as we said before, we're going to focus on ionic reactions as opposed to radical reactions, meaning that our bonds are going to be broken heterolytically. And so then these reactions are driven between these sort of equal and opposite forces, of positive charges being attracted to negative charges, right? That's largely what this concept of nucleophile and electrophile is all about, okay? A nucleophile is electron rich, okay? A nucleophile, let's pick it apart. It loves, phile means love, it loves a nucleus, right? And again, that's because it's electron rich. So it really wants that positively charged nucleus. So nucleophile, nucleus lover. And again, nucleophiles are going to be electron rich. There's going to be a few categories of nucleophile that are going to be easy to spot. So one is when you have a really polar bond. This is what's called an organometallic compound. This is lithium, which has a super low electronegativity. We don't really think of carbon as an electronegative atom, but when you compare it to a metal like lithium, it very much so is. So in this type of compound here, there will be a partial negative charge on that carbon. That carbon will be electron rich. We're not going to cover organometallic compounds this semester. More common nucleophiles that we're going to see are sort of more obvious electron-rich species. So for example, an ethoxide ion, something with a negative charge on it, right? That negative charge would really like to find itself a positive charge. Another example, so negative charge, as well as just lone pairs. So again, my nucleophile here would be by oxygen because of these lone pairs here. We're going to see alcohol groups and oxygen and water playing the role of a nucleophile. And then another one would be a pi bond. So it turns out that we're going to see reactions where the pi bonds of alkenes act as nucleophiles. And then, you could think back to this idea of a Lewis base, which was something that was sharing pairs of electrons. So what's the difference between a nucleophile and a Lewis base? Nothing. They're the same thing. They're just different terms. But yes, a nucleophile is something that's going to be donating its electrons just like we thought of with the Lewis base. Electron rich is what you want to have in mind when you think of a nucleophile. So what's an electrophile? That's just the exact opposite. It's an electron lover. Okay, so this is electron deficient species. This is something that really wants electrons. So how do you get electrophiles? So similarly, you can see them through induction. Although this is, you don't need something like a metal for this. This would be true if you had a carbon-halogen bond, or even something like a carbonyl bond. If I'm going to just sort of keep color coding here, my electrophile in this case would be the carbon that sits on the other end of these polar bonds. Okay, so induction / polarity could lead to a electrophile, as well as a famous electrophile that we're going to see throughout this semester is the carbocation, because it has an empty p orbital. Right? The positive charge itself is kind of a giveaway that it would like electrons, but we have to be careful because something like a positively charged oxygen cannot accept a pair of electrons because that would violate its octet rule. So really what's key about this carbocation is the fact that it has an empty p orbital. That's what's going to make it a good electrophile. It can accept electrons. And it is, again, just a Lewis acid. Like the terminology is one and the same. It is something that can accept a pair of electrons. So now, given molecules, we want to be able to identify, keep colors here, nucleophiles and the electrophiles, okay? So again, nucleophiles means that there are electrons to donate. So ammonia with its pair of electrons would be a great nucleophile. Negative charges are great nucleophiles, right? They really want to find a positively charged nucleus. That would be an example there. And we said double bonds. This might be the most counterintuitive one. We'll see, you know, when we get to this point, we'll see. But these will also be, okay? And furthermore, with the lone pairs, right? So alcohols can play the role. Carbonyl oxygens can play the role of nucleophiles. We will see that actually carbonyl oxygens are not quite as strong of a nucleophile as alcohols. But for now, let's just worry about classifying them kind of roughly. There are certainly acid-base reactions that we saw carbonyl groups playing the role of nucleophiles. And then again, this oxygen right here, I'm not going to call a nucleophile, even though it does have one pair of electrons, right? Both of these guys have two. This does have one pair of electrons, but it's already got a partial positive charge, meaning that it's not going to give up that pair of electrons at all. Okay, so that would not be a nucleophile. So then what about an electrophile, right? So now going through and assigning our electrophile. So I guess I'll actually include this one as well. Although hopefully you can tell that this is going to be much stronger of a nucleophile because it actually has a negative charge. All right, so then what about the electrophiles? Well, this carbonyl carbon is again an electrophile, something that we're going to see play the role of an electrophile quite a lot. Carbonyl carbon, same down here. Right? So notice that this molecule right here had both an electrophile site and a nucleophile site. That's totally possible. Our carbocation is going to be an electrophile. And then this carbon in a carbon in an alcohol bond is also electron deficient because of that polar carbon-oxygen bond. So then this compound here is kind of a weird one. You do have that, I did this example sort of specifically, one to caution that you might be tempted to think of, because it has a positive charge, we want to call it an electrophile, right? It has a positive charge, so of course it wants electrons. Yes, but the problem is that it has a full octet. So it's not going to be able to accept any new electrons. Oxygen will never exceed its octet rule. So this is not going to be an electrophile. However, we can see if I drew the other resonance structure here, where this pair of electrons jumped up here, what I would be left with, I'll just sort of erase and draw it on there. This pair of electrons jumps up here. That means that I get rid of my positive charge. It just becomes a pair of electrons, and I'm left with a positive charge on that carbon. So this would be an electrophilic site in this molecule. And this is just another resonance structure. So if I kind of undid that resonance drawing here, we would still think of this carbon right here as an electrophilic site. All right, so you want to be able to spot nucleophiles and electrophiles. That's going to be step one here. How we go about using them in reactions and all that good stuff, that will be the subject for later, but make sure that you can actually spot nucleophiles and electrophiles. Again, with nucleophiles, you're looking for either induction, leaving a partial negative charge on that carbon, a lone pair, especially when it has a negative charge, or a pi bond. Those would all be nucleophiles. An electrophile would be also, at the end of a polar bond, but this time the one with a partial positive charge, or any compound that has an empty p orbital. Those are also good electrophiles.